all of that work that we did is nice and all, except that we did it for just one axis, right? One axis. If we want a different axis, say one through the middle, got to do it all over again. Right? Set it up from a new axis. Now, you don't have to do all the work over again. It will really depend on the nature of the problem. But in many cases, you might have to do the work over again. In this problem, we probably don't. I think that we could probably all see that we can point to this box using X like we did before. If our pointer still works, we can probably use all the other work we did. We probably just have to change the limits. So instead of starting at 0 and going to L, we would start at maybe negative L over 2, half the bar, and go all the way to positive L over 2. And that would, give us our new moment of inertia. I will say that there is a shortcut out there. We're going to learn it. It's called the parallel axis theorem. And it allows us to shift the axis from one place to another. But it's limited. It's the parallel axis theorem. So it allows us to move the axis to a parallel location. Now, what I mean by that is, think of the door. The door has an axis through the hinge. And although you might not believe this, if you were to be above the door and you looked down on the door is a bar, right? It's rotated this way. So the door is a bar. Even though it's really long, a point here is the same distance away from the axis as that same point up here. So it has symmetry. So although we proved the moment of inertia for a bar, a thin bar like a meter stick, it applies to a thick bar as well. Now, we have the moment of inertia about, the hinge. Now, we could shift to another axis, say here, using the parallel axis theorem. But we couldn't, put a peg in a door here and spin it this way and use the parallel axis theorem, because that axis is not parallel to this axis. Does that make sense? So the parallel axis theorem allows a very simple way of shifting the axis, and we'll talk a little bit about it next week, but more so the week following. But it's not a panacea. In many cases, if you want to spin something in a much different direction, you've got to start the problem back over from 0. So that being said, let me first take a moment and talk about the fact that there are a lot of objects to whom the moment of inertia is well known. And if you've looked in your book, you know there's a table of moments of inertia. I'd like to talk about some of the basic shapes that I think would be incumbent upon you to memorize. And you don't really have to memorize very much. You'll see what I mean in just a minute. Let me just draw them all out. The table in your book has more than just these, but this is, if you look at all the AP exams, these shapes show up the most. And to kind of put these in perspective, I've got a ring or hoop. So something that's thin. So it has, radius, r. And I'm talking about spinning all of these about their center. The ring or hoop has a moment of inertia of mr squared. The mass of the hoop times r squared. Then there's a disk. So this is a thin or thick disk. So it doesn't matter whether it's a really thin disk like a CD or a record, or if it's a can like a soup can, but soup won't work because it's got a liquid inside. So something that's solid, a solid cylinder. If you're rotating about its center, it's still going to be the same moment of inertia, which is 1/2 mr squared. Then we've got spherical objects. So there's solid spheres or a hollow sphere. So a solid sphere like a golf ball, bowling ball, even a baseball, softball not so much, but they would all have a moment of inertia of a solid sphere, which is 2/5 mr squared. Again, we're talking about spinning it about its center. And a hollow sphere is 2/3 mr squared. And of course, the bar about its end, 1/3 ml squared. These are some of the basic shapes. They're composites, and the parallel axis theorem works for all of them. We see discs all the time because all of our pulleys are discs. We bowling balls, so we'll have things that roll. You know, you guys, soccer ball or a volleyball, that's going to be a hollow sphere. So we tend to see these a lot. If you ride a bicycle, well, your wheels are likely hoops. The spokes don't really matter that much. Almost all the mass is on the outside edge. So it's amazing the number of things that you can actually create from these basic shapes that end up being, you know, just parts of a composite. So, you know, the human body's kind of a couple of these, you know, arms and such, torso, legs, with maybe a one of these for the head. And although, yeah, that's probably an overgeneralification, probably a little bit of a simplification. Yeah, but how close do you have to get sometimes? You know, in some cases, you can get really close to how a system will behave. Now, for an irregular shaped object, you're going to have to measure it empirically. You have to give it energy and see what the resulting velocity is. In all cases, the thing I want to emphasize here is that objects have a moment of inertia, and the calculation of the moment of inertia is not insignificant. And because of that, if you want to calculate rotational kinetic energy, one of the first things you'll have to calculate is moment of inertia first. Almost every angular quantity is going to involve the moment of inertia. So I'd say that from this point forward, there's 2 steps for doing a lot of rotational work, because you'll have to deal with moment of inertia first and then use it in a calculation later. I have no idea what that noise is.
Percussion.
Is it? What are they? They tuning up? All right. What I did in 4th period is I gave them the option, but I'm not going to give you guys the option because we are probably going to be interrupted any moment. I want to talk to you about, I want to do another one of these while it's kind of fresh in your head. And the one I'm going to do is purposely more difficult than the last one. There's not many simple options out there. The bar is the simple option. Now, a hoop, which we could do next, is actually simpler than a bar, because you really don't have to do any work for it. And so I don't really want to do the hoop in any real detail, because remember what moment of inertia is. It's a measure of how the mass is distributed. And it's a sum of how far away each piece of mass is from the axis of rotation. Well, if I were to just pick out 3 pieces of mass, say that piece, and this piece, wouldn't you agree that they're all the same distance from the center? In fact, I would go as far as to say, isn't every bit of the mass of a hoop the same distance from the center? So that's why its moment of inertia is just mr squared. Now, yeah, I can do the calculus if you really need to see it, but that doesn't really, it's not a real exercise. If you want to really see how this works, then let's pick a real shape, a shape that has potential to be interesting. And so what we're going to do is the disk. And we'll do a disk about its center. And part of the reason I like doing the disk here is because the disk, it's going to teach you something that I don't think you've ever thought of before. So we'll see how far we get with it. I'm going to go through the series of steps that we had before. And I want to remind you that in doing this process, one of the things we have to do is kind of define the parameters of the size of our disk and then pick a piece of it someplace. So let's pick some parameters. How about radius, capital R, and a mass of M? Since this is a disk, we're not going to be able to do linear density, but we'll probably do surface or areal density, meaning the mass per meter squared. But I think you guys already know that. It's going to be m over pi r squared, right? That's the mass per unit area. I'm throwing that out there because if I wanted to figure out how much mass a piece of it had, I'm probably going to need this like we did yesterday. So let's figure out a piece of it. I'm going to choose a piece, say right there. Not quite on the edge, somewhere in the middle, but far enough away where I can make my point. That's the piece I'm going to choose to look at. And again, it's a piece of the whole mass. So it has mass dm, right? Delta m, a piece of the mass. Now, this isn't linear. It's an area. So if I want to make this comparison, like I did before, it would be dm on the top, but on the bottom, I would probably have to have length times width, right? To find the area of my box. Does that seem like a good way to go? Length times width? All right, so we're going to use that as our ratio later. We'll solve it for dm and all that in a minute. Now, if you don't, yes, sir. It is squared. Don't you see the 2 there? I don't know. Maybe I didn't draw it clear enough. No worries. I can see how you would have mistaken that. Good call. Thank you. That's what I can always count on my students to keep me honest. All right. So you remember the next part of this is we had to find a way to point to that object. And here's where it's going to get a little screwy. That's because when we were dealing with a one-dimensional object, pointing to any part of the object wasn't all that hard to do. The object was in a straight line, so if I wanted to point to a piece of mass, all I had to do was draw a line to it and say it's right there. This is not as easy because I need to find, a way to point to that piece. So I'm putting together a reference. I could use a Cartesian method. Say, go out a distance x and up a distance y. I could do that. And I could define the size of this piece by looking at x and y. I'd probably want to turn my piece so it's lined up with x and y. That would make it easier. But I have another option too. I could point at this piece by going out a certain angle, theta, and then walking out to it. Now, I'm going to walk out to the first corner, just like I did on our exercise yesterday. We walked to the first edge of the piece. I'm going to the first corner of the piece. Now, I'm going at a distance r and angle theta. Now, which one of these is better, x and y or r and theta? And the answer is elusive. It's not obvious why one of these is better than the other. The easy way to give you this answer is to just say it simply like this. If the object is square or has corners, use rectangular. And if the object is circular or has curves, use polar. That's typically it. But the real thing is you're never probably going to do this again. You'll probably only do it for the disk. So we're going to use polar. And the reason why that choice is actually made, if you're interested in like the whole theory behind it, is that if I chose to use x and y, then every choice for x is a different limit on y. For example, when I'm picking this x right here, y goes from here to here. But if I'm picking, say, this x right here, well, then y goes all the way to there and all the way to there. So every choice of x requires different limits on y. On the other hand, if I use polar, any choice of theta, I have the same limits on r. It goes from 0 to the edge. Does that make sense? So when I'm choosing one of these, you choose it based on which shape lends itself best to the parameters you have. And for us, the parameters that work best are going to be polar. Now, if you remember what we did yesterday, we then had to describe the size of this piece using our measurements. Yesterday it was just x. Today we have to describe the size of that piece using r and theta. Now, judging by what we did yesterday, if you'll remember, and I'm going to kind of zoom in on this. If you'll remember, we went out a distance x, and then we said that this length right here was just a little bit more than x. I'm going to do the same thing here. I'm going to go out a distance r, and I'm going to say that this length from here to here is just a little more than r. I'll call it dr. Is that okay? Any problem with that? This one's going to be harder. I'm going to do this side next, where the width is. Now, this one you may not follow through with, but imagine if I wanted to trace the edge of this arrow and have it draw the length of W. So I'd have it like draw along here. What I'd actually be doing is saying go out a distance r and then just slide a little bit around. It's an arc length. So imagine you have you're doing a compass. You go, right? I'm leaving r fixed and I'm just drawing a small piece of the angle. Now there's a precedent here that I used yesterday that, remember, if you remember, delta x equals delta theta times r. Do you remember that from like 3 days ago? That's what we're using here. We're going to say that that width is r times d theta, a piece of angle times r. That's the arc length, and that defines this piece. Is that okay? I know it's a little complicated, but again, it's just that little arc length. I'm sticking my finger out there and I'm moving d theta over. D theta is the piece of angle that I'm moving. Can we be okay with that, or do I need more explanation? Now, I want you to watch this for a minute. This is going to help you, I think, in a minute. The area of that piece, if I want to shade this piece in, the area of that piece has to be length times width, or dr times r d theta. That has to be the area of the block. That okay? Right? Length times width. dr is the length, and r d theta is the width. I really want you to see this, so I'm very driven for this. But are we okay? This is length, this is width. Can I go on? All right. This has never been shown to you before, so I want you to see this because I think it'll help with what we have to do next. If what I'm doing is right, if this works, then if I wanted the area of the whole shape, I would just have to add all the areas of the boxes. Meaning, bear with me, I would have to sum all of the drs and all of the d thetas. That's how calculus is supposed to work. Now, a reminder, when you look at this, things that have theta in them have to be near d theta, and things that have r in them have to be near dr. So I'm going to remind you that we can multiply in any order as long as they're not vectors. And these are not vectors. So I can put the r in front of the dr because it doesn't matter what order you multiply. And I know that seems weird to you, like they have to be grouped together this way because one's length and one's width. But once we're multiplying things together, it doesn't matter the order in which you multiply. So I'm going to rewrite this as r dr times d theta. And I'm leaving a little space because I want to add up all of the drs and I want to add up all of the d thetas. I know it looks a little weird, but I want you to think it through. I'm going to start at, I'm going to start at theta equals 0. And I'm going to add every box from the middle of the page, the middle of the disk to the edge of the disk. And then I'm going to go to the next angle. and add up every box from 0 to the edge. And I'm going to go all the way around my disk. So how many radians will I have to go around to go all the way around my disk? 2 pi. Now I know there's 2 integrals here. It's a double integral. Because I am integrating an area, there has to be a double integral because areas have length and width. If it was integrating a volume, there'd be 3 integrals, length, width, and height. So a double integral just tells us that we're integrating an area. That's all it is. We had a single integral before because it was one-dimensional. Is that okay? So this is a pretty easy double integral. They are harder ones in life, but this is not one of them. We can just do them individually by themselves. Like I can do this one right here by itself over there. I'll point out that this is r to the 1 power, and I'm taking my integral with respect to r, so r is the important variable, and it's a polynomial, so I can use the polynomial rule, which means add 1 to the exponent and divide by the new exponent. That gets rid of the integral symbol, but I have not yet applied my limits. Okay so far? All right, let's do the theta. There's no theta in front, so we assume that it's theta to the 0 power, because theta to the 0 is 1. That's the implied number that's in front of d theta. It's a polynomial, so I use the polynomial rule, add 1 to the exponent, and divide by the new exponent. Get rid of my summation symbol and apply my limits. Now you notice that both limits are 0, right? On the bottom end. So I'm not going to write those in. I'm just going to put in my limits. And my limits will be r squared over 2 times 2 pi. Do you see it? Do you see the 2's canceling? And I'm left with pi r squared. It looks familiar, right? Now, I don't know about you, but it's probably never been proven to you why the area of a circle is pi r squared. But this is why the area of a circle is pi r squared. This is a valid calculus level proof of where pi r squared comes from. And it's quite literally taking the area by adding up all of the different blocks that make up a circle. Now, I think that's pretty cool. But also, I've seen it before, so maybe I'm just a math geek. Now, I did all of that work because I wanted to make sure you understood that over here, when we solve this for dm, and we have m over pi r squared times length times width, that this dm should add up every box that takes over the whole circle. And I've proven that doing the sum will encompass the whole circle. Okay so far? All right. So let's apply it to moment of inertia. And we already know what the answer is supposed to be. I gave it to you a few minutes ago. But we're just trying to verify it. To use this, we have to recall that moment of inertia is a sum, and there are 3 parts to the sum. There's the dm, there's the perpendicular distance squared, and then there's the summation portion. So I'm going to substitute in for dm, m over pi r squared, dr r d theta. That's substitute in for dm. I'm using the same variable name for the perpendicular distance, right? The default one that's in the formula is r squared, but is that the perpendicular distance already? Yeah, that's the same symbol. because r is the perpendicular distance from the center to where my square is. So in essence, this r and that r are the same r's. Now, the only thing I have to do different from the last time we did this is I have to remind myself that there are two sums. There's a sum for the angles, and there's a sum for the r's. Okay, so far? All right. I have to collect all the things that have to do with theta and put them with the summation for theta. And there really isn't anything besides d theta. And then I have to collect all the things that go with r and put them with dr. And there's just r cubed, right? R squared times r is r cubed. And I put them with dr. And all that's left are things that have nothing to do with where we are on the disk. I want to set my limits by choosing every single box on the entire disk. Good so far? All right, we did all the heavy lifting. That's it. The next part is just executing the integral. And although I know that's new for a lot of you, it's really not that hard. We already did this one. This one we've already done all the way. It's just going to be 2 pi again. Do I have to do all the little steps in between, or am I okay with not doing all the little steps in between? You tell me. We're good to go? This one, polynomial rule. I have r cubed, so I'm going to increase the exponent by 1 and divide by the new exponent. I still have to apply my limits. And I'm going to bring down the m over pi r squared. Okay, so let's apply the limits now, because we're really almost done. I've got m over pi r squared. I've got r to the 4th over 4, and I've got 2 pi. Collect all the terms. Like, I can cancel out the r squared on the bottom. I can cancel out the 2 with the 4, and I can cancel out the pi's. And I'm left with 1/2 m r squared. Now, look, I'm not going to minimize how much work this is. This is a lot of stuff, and there's a lot here. And I do not expect you guys to be masters at this. I do think it's accessible, though. And although we've done all the work for it, I say I directed most of it, and I will not for a moment think that if I just threw this at you right now, you'll be successful. But at the same time, there's only a couple shapes that we can actually do. We can only do the 2-dimensional shapes because we don't have 3-dimensional math yet. So the 3-dimensional ones are out. The only other one we haven't really done that's here is a thick ring. One that has doesn't just all the way, it's not on the edge, but a thick ring. That one we could do because it's similar to the disk. It's just that my limits would start a little further out. And we didn't do a square. We could do a square or a rectangle. We might do one of those. Now, there are more interesting, if you're interested in this, then if you've ever spun a coin, like on a tabletop, that would be spinning it about an axis like this. That's actually pretty interesting math. If you're interested in seeing interesting math, that would be it. This is not particularly interesting. After you guys have moved on in math a little bit, you'll find that this is actually rather pedestrian. However, in real life, things don't have uniform densities. Often the density is different from the inside to the outside. If you wanted to find the moment of inertia of Jupiter, Well, Jupiter's more dense at the center than it is at the edge. So if you treat it like a solid sphere where the density is changing, you get really different results. So for people who are in astronomy who want to model things, they often have to do something like this, a calculation where the density isn't uniform. And that makes for more interesting math. So that's probably